Welcome to this presentation on the weighted residual formulation, specifically the Galerkin method we're looking at here. Looking at the roadmap of where we've been, we've done the direct formulation, the minimum total potential energy formulation, and introduced the weighted residual formulation, but done specific with collocation and subdomain, and then this one we're looking at, the last one, the Galerkin's method. All right, so going back to our example, we have our beam and bending, expected to have some type of smiley face shape. We got the two boundary conditions, and we have our governing differential equation. So what we've already done in the first video, so go back to if you want to see that, haven't seen that yet, look at the introduction piece. We've done 1 through 4 here. So now we're on number 5. We're going to force the residual to be 0 at various points or intervals using the different methods. So that, we're going to take the residual function that we have here, and we're going to the reason we again have R is this is our governing differential equation. Normally it would be equal to 0 on the left-hand side here, but because there's going to be some error, because we've assumed some solution, so there's going to be some residual, some error that we have to account for. And so the equation we're going to be working with, our overall residual equation, is this one where we've now substituted for the second derivative of our assumed solution. All right, so let's go see how that works for Galerkin's method. All right, so in this method, the integral of the residual equation is multiplied by a weighting function. All right, so this is the new piece here, right? Weighting function. And then we're going to force that equation to be 0. The weighting functions are chosen to be the same form as each part of the approximate solution. All right, so let's see what that means. So here's our Galerkin's method, the initial equation. So we have the interval we're going from 0 to L. So it's across our whole this would be the whole element, or in this case, our whole beam. So you do this element by element. We have the weighting function, so that's where that shows up. And then we have the residual. And the I, the subscript there, depends on the number of unknown coefficients. We only have one. We just have A we're trying to find. So we don't have to worry about one of these equations. So in this example, because it has to be the same form, right, we want our weighting function to be the same form as the approximate solution. It's going to be a sine pi x over L. We're not going to include the A because we don't want to have to find another unknown coefficient. So we're going to substitute that in. So for our weighting function, that's going to come down and be our sine pi x over L. And the residual function is the one from before, so this is all our residual. And we're going to integrate that all with respect to x. And that's all going to be equal to 0 because that's what we're forcing it to be 0 over this interval. So as we do that, our A, our unknown coefficient, is found to be minus 4 times the moment L squared over pi cubed modulus times the moment of inertia. Right, so ultimately we take our unknown coefficient, substitute it back into our assumed solution equation. So basically we're just substituting right here for A. This is what we come up for a deflection equation. All right, so that's one way of doing Galerkin's method. Another way is, well, I guess it's the same way, but it's with a third order polynomial here. And we're going to have 3 weighting functions. So we have 3 parts, 3 unknown coefficients, right? We got A is unknown, B is unknown, and C is unknown. Therefore, we have weighting function number 1, 2, and 3. Note how they are. We got just x squared, and x cubed there. So as a result, we would have 3 equations to solve for A, B, and C. So we'd have weighting function number 1, which is just our x. And our weighting function number 2, which is our x squared, weighting function number 3, which is our x cubed. And we do each of those over the same interval. It'll all be from 0 to L, and we'd use the same residual equation for each of those. All right. So the Galerkin method is actually one of the more common ways of solving finite element solutions. So we have the exact solution we did back in the introduction. We have the collocation, we had the presentation on the subdomain method, and here's the Galerkin method we just came up with. So these are all the deflection equations. This should be y, and that should be x. But anyway, so this is the equations we came up with in the end of each presentation, so we can see how they compare. And if we're looking at the exact one, right, it looks like Galerkin seems to have probably the best. If we're looking at everything else, is the moment times L squared over EI is the same for each one of them. We got 0.111, 0.112, and 0.094, 0.091. All right. Subdomain is very close to. Collocation seems to be a bit off. from these values, but overall you can see what the comparison looks like between each of the methods that we used. All right, again, I'm going to go to an example here following this one, this presentation, where you can see I'm going to use all of them with a different assumed solution, and you can see how those things turn out.